Alright, in this video we're going to talk about Unit 10, Objective 2, Volume of Rotation. So what we're going to be doing in this objective is we're going to be taking a curve, or an area in between two curves, and rotating it around an axis to form a three-dimensional figure, and we're going to try to find the volume of that three-dimensional figure. So what this could look like would be this right here. If we have the curve y equals the square root of x and y equals x squared, so you can see those in a three-dimensional plane. The area in between them is kind of colored in with that yellow-brown color, and you see a random rectangle colored in red. So what we're going to be doing is we're going to be taking that area and we're going to be revolving or rotating that around an axis. In this case, we're going to be rotating around the x-axis. And when we do that, we're going to make a solid figure. In this case, it looks like that. And we're going to try to find the volume of that solid figure. So what we're actually going to be doing here is we're going to make a bunch of washers. So what we can do is, if we take just that one rectangle, we can rotate just that one and kind of see what's going on here. If we rotate that all the way around, you can see a washer, not like a washing machine, but like what you use to help fasten screws. So you see the washer there. What we're going to end up doing is finding the area of the outer radius, finding the area of the inner radius, and then subtracting them. So if we were to find the area of the outer radius and just that, and we rotate it, that circle on the inside is not going to be there. And then if we find the inner radius, that circle that's just the circle. So when we subtract out the inner radius, we're basically taking that circle away. So we're going to be, again, making that solid by rotating a bunch of washers that make up all of the volume for that shape. So how we're going to do that is pretty simple. We just need to know one little formula, and it basically comes from the area of a circle, pi r squared. What we're going to do is we're going to multiply pi times an integral from a to b of our outer radius, so we'll call that capital R, outer radius, minus our axis of rotation squared. So there's our radius minus our axis is like the radius of the washer, so there's the r squared, and we can pull the pi out front, so pi r squared. And then we're going to subtract the inner radius, so we'll call that little r, minus the axis, and square that. And then this is going to be, I'm going to write dx, but it could be dy depending on which way we decide to integrate. So we're looking at the integral from a to b of the outer radius minus the axis quantity squared minus the inner radius minus the axis squared, and multiply all of that by pi. So using that example that we had a second ago, let's say find the volume of the solid formed by rotating the region bound by y equals square root of x and y equals x squared. Sorry, y equals x squared. Rotating that region around the line y equals, say, 3. So what this would look like, so just a quick sketch. Square root of x looks something like that. X squared looks something like that. So our a and our b are going to be where those two graphs, those two functions intersect. So this point here, we're going to say 0, 0, and I'm doing these in separate colors for a reason. We'll talk about that in a second. This other intersection point here is going to be 1, 1, and again I'm going to use separate colors, and you'll see why in a minute. So the area in question that we are rotating is going to be this area here. So we're going to take that thing and we're going to rotate it around the line y equals 3. So y equals 3, so this is 1, 2, 3. Obviously this is not drawn to scale, but we have this line y equals 3, and we're going to try to rotate around that. So a trick here is our rectangles, so I'm going to put a little note over here, that we want our rectangles to be perpendicular to our axis of rotation. So when we go to build the rectangles that we're spinning, we want them to be perpendicular to the axis of rotation. So if our axis of rotation is horizontal, our rectangles need to be vertical. So I kind of drew in a rectangle there. Now we're going to want to take infinitely many of these rectangles, and we're going to want to build them from here all the way down here, all the way to that other point there. So this is how we're going to build our outer radius, inner radius, and all of that fun stuff there. So to find this, we're going to say the integral, or pi, times the integral from. Now we want to build our rectangles from the left to the right. So we want to start all the way to the left, so that's going to be 0. So I'm taking a blue 0 there. And we want to build all the way to the right, so that x value of 1. So we want to use x values when we're rotating this way. Then we need to think, what is our outer radius? So what is the part, or what function is farthest away from our axis of rotation? So in this case it's going to be x squared. So our outer radius, x squared, minus our axis of rotation, so minus 3, quantity squared, minus our inner radius is going to be the square root of x, because that's closest to our axis of rotation, minus our axis of rotation, quantity squared, dx. Now we could do that by hand, we could use a calculator. We're going to kind of skip that in the interest of time, but that's how we're going to set this thing up. Now we could also ask the question, take that same area, instead of rotating our area around y equals 3, we could say let's rotate this around x equals 3. So we can keep the same areas there. 1, 2, 3, again, not drawn to scale, but this time we're going to be rotating around this axis here. So if our rectangles need to be perpendicular to the axis of rotation, my rectangles are going to be horizontal this time. So I'm going to be building my rectangles like this. So when we think about our integral, our answer for this one, we're going to say pi times the integral. Now this time we're building from the bottom up. So instead of taking the 0 that's blue, because that's an x value, we're going to take the red 0 to the red 1. So we're dealing with y values. Now since we're dealing with y values, we need to integrate with respect to y. So when we integrate with respect to y, we want to take our original functions and we need to change them. This is going to turn into x equals y squared, and this is going to turn into x equals the square root of y. Those are our new functions. That's what we're going to want to use for our integration, because we have to go with respect to y. And we know we have to go with respect to y because our rectangles that fill our area are going to be going from the bottom to the top, so they're going to be dealing with y values. So we need y values inside our integral. So again, now we just need to think about the formula that we have at the top, our outer radius, so the part that's farthest away from our axis of symmetry. Farthest away from the axis of symmetry was our square root of x, but now we're turning that into y squared. So it's y squared minus our axis of symmetry, so minus 3 quantity squared minus, then we have to do our inner radius, so in this case it's going to be square root of y minus 3 quantity squared and then dy. And again, you could integrate that by hand, you can do it with a calculator, but for the interest of time we're going to stop there. So we always want to think the outer radius, so the thing farthest away from our axis, minus our axis quantity squared, minus the inner radius, or the part that's closest to our axis, minus the axis quantity squared. The things we need to be careful for are when we are going to be rotating around a vertical axis, we need to integrate with respect to y. So we have to change our original functions from y equals to x equals. Other than that, it should be pretty straightforward. And that'll do it for this video. We'll see you in the next one.